Good afternoon. Good afternoon. Yeah?
Yeah.
Okay, thank you. Again, thank you for coming back to the last session of this workshop. And this time we will have the presentation of a book about mass spectroscopy using particle accelerators. But I don't know if it will be given in Spanish. I think so, mostly in Spanish. So
Yeah.
please be patient. And we will start with Dr. María Esther Ortiz, who will make an introduction, present an introduction about the book, un prólogo del libro.
Yes. As a presentation of the first book of LEMA, I will allow myself to read you the prologue written by Rosaura Ruiz, to whom it was not possible to contact, surely because her multiple duties that she has now. El laboratorio, well, I have to apologize, no, I didn't translate it. El Laboratorio Nacional de Espectroscopía de Masas con Aceleradores, LEMA, una de las joyas del Instituto de Física, pero también del Sistema de Investigación de la Universidad Nacional Autónoma de México, surgió a partir de la iniciativa de un grupo de investigadores de física experimental que, con gran visión y dándose cuenta de las enormes posibilidades que un laboratorio de esta naturaleza abriría para toda la comunidad académica mexicana, obtuvo inmediato apoyo y financiamiento por parte de las dos instituciones más importantes de nuestro país dedicadas a la investigación, a la formación de noveles científicos y a la generación de nuevos conocimientos, el CONACYT y la UNAM. Es así que a los pocos años de surgir como una idea sumamente prometedora, este proyecto se concretizó el año 2013 al inaugurarse sus instalaciones, convirtiéndose así en el primer laboratorio en utilizar la tecnología EMA para el análisis de radiocarbono en nuestro país y el primero en Latinoamérica capaz de analizar los isótopos de berilio 10, aluminio 26, yodo 129 y plutonio. Ha pasado menos de un lustro desde su apertura y el LEMA ha devenido ya en una herramienta de invaluable utilidad para dos de las tres actividades fundamentales de nuestra universidad, pues en él la enseñanza y la investigación se ven enriquecidas y consolidadas gracias a un trabajo que redunda en la aplicación práctica de los conocimientos teóricos y en el empleo útil y concreto de los resultados obtenidos en sus mediciones, generando así sinergias, colaboraciones y conocimientos de gran relevancia, tanto para el sistema de investigación de la UNAM en su conjunto, como para los beneficiarios de sus resultados. Un ejemplo de lo anterior es el taller de Física de Radiaciones 2 de la Facultad de Ciencias. Realiza la preparación y análisis de muestras con radiocarbono para fechamiento mediante técnicas radiométricas, aprovechando el equipo preexistente del centelleo de líquidos y con el apoyo del Laboratorio Nacional de Espectroscopía de Masas con Aceleradores LEMA. Una colaboración que también ha permitido que tanto el taller de investigación denominado Preparación de Muestras Geológicas y Ambientales para Análisis y Fechamiento con Carbono 14, dirigido a los alumnos de las carreras de Ciencias de la Tierra, Física, Física Biomédica y Biología, así como los servicios de análisis radiométricos y de preparación de muestras para análisis mediante AMS, y el taller de Radiaciones 2 oferta a investigadores, usuarios externos a la Facultad de Ciencias que tengan el respaldo y el aval del LEMA. A esto cabe añadir que la labor realizada en el LEMA trasciende el horizonte propiamente académico, pues también se ofrece como un servicio profesional que se presta a científicos de muy diversas áreas disciplinarias, coadyuvándolos en sus estudios al analizar muestras convenientes de tan diferentes matrices y contextos, como lo pueden ser aquellos de interés arqueológico, antropológico, ambiental, geológico, astrofísicas, forenses, histórico, médico, químico, biológico o los relacionados con el mundo del arte. De este modo, el LEMA ha logrado hacer realidad en su quehacer diario el tipo de trabajo considerado modelo ideal en nuestros tiempos, aquel que de carácter transdisciplinar que apoya al mismo tiempo estudios de ciencia básica y de ciencia aplicada, a la par que proyectos académicos de carácter humanístico y social. Una finalidad original del LEMA, espacio privilegiado y hoy por hoy un laboratorio en la más amplia extensión de la palabra, pues en él se desarrollan trabajo experimental paralelamente que se efectúan labores de enseñanza, aprendizaje teórico-empírico, investigación, presentación de servicios y se generan nuevos conocimientos. Fue propiciar el acceso de la adaptación con radiocarbono mediante espectroscopía de masas con acelerador a la más amplia comunidad académica posible. Lo que poco a poco lo que en poco tiempo de entrar en funciones logró con creces expandiendo gradualmente su alcance y abriendo horizontes de aplicaciones de sus tecnologías, sin afectar con esto la calidad de sus productos. Un éxito que pocos proyectos pueden presumir de tener a corto plazo y que se debe por igual a sus instrumentos de vanguardia como a la calidad y talento de sus operadores. Perdón. Por si fuera poco lo anterior, el LEMA nos ofrece ahora este libro que tenemos ante nosotros y que promete ser el primero de una serie donde mostrará fehaciente y puntualmente las enormes oportunidades que abre el contar con una técnica de espectroscopía de masas con aceleradores EMA para nuestros estudiantes, investigadores, académicos, instituciones y sociedad en general. Un fruto editorial que busca convertirse en una herramienta pedagógica, didáctica y en última instancia vocacional de referencia, para lo cual nos ofrece una introducción al universo de las capacidades y potencialidades prácticas y temáticas de este laboratorio, donde el microcosmos y el macrocosmos se encuentran por medio de la experimentación y manipulación de los isótopos cosmogénicos presentes en materiales naturales, terrestres y extraterrestres, lo que resulta ya de suyo fascinante. Un libro que es una ventana al quehacer del LEMA y una mirilla hacia el conocimiento y comprensión de lo diminuto del universo subatómico, de los secretos que en él se guardan y que ahora tenemos la capacidad de desentrañar. Este libro es entonces un fruto de trabajo colectivo, con enfoque didáctico, fondo científico, forma divulgativa y de contenido trans, multi e interdisciplinar, que nos llevará desde la descripción de cómo se obtienen las muestras para el laboratorio, pasando por cuestiones técnicas en relación a la separación isotópica y hasta temáticas de índole antropológica, forense, de astrofísica nuclear o relativas al patrimonio cultural, lo que nos habla de la vastedad tan rica cuan interesante de este documento, que es reflejo fidedigno del espíritu del LEMA y de las personas que le dan vida mediante su entrega diaria llena de vocación, una profundísima pasión científica y un compromiso incuestionable con la formación de nuevas generaciones de investigadores capacitados en el empleo de esta tecnología, que, como hemos dicho, tiene la cualidad de abrirnos la posibilidad, si no de viajar en el tiempo, sí de obtener respuestas y evidencias sobre la historia de los más insospechados materiales, lo que finalmente se reducirá en la satisfacción relativa de algunas de las aspiraciones que insuflan a toda persona dedicada a la indagación científica. Y esto mediante el esclarecimiento de algunas dudas, la revelación de mayores áreas del espacio ignoto que rodean nuestros objetos de estudio, la solución de ciertos acertijos y el descubrimiento de nuevas vías que nos permitan avanzar en la comprensión de las problemáticas que nos hacen frente, de manera tal que estemos mejor preparados en nuestro constante intento por superarlas. Rosaura Ruiz Gutiérrez. So, I want to invite you. Gracias. I want to invite you to collaborate writing one of a new chapter for the second book. Thank you.
Muchas gracias a la doctora María Esther Ortiz. Ahora tendremos la participación de la doctora Corina Solís para describirnos el contenido del libro.
Sí, gracias, Javier. Buenas tardes, gracias por venir a escucharnos hablar de este libro. Bueno, me corresponde a mí hablar un poco de los capítulos que contiene, son 11 capítulos. Después de la introducción tenemos un capítulo que habla de los aspectos básicos de la técnica de espectrometría de masas con aceleradores. También el capítulo 2 es más técnico, habla sobre las características del separador isotópico del LEMA. Después viene un capítulo del error asociado, de cómo se hacen las correcciones, qué tipo de correcciones se pueden hacer a los datos que arroja el acelerador, si se hace por corrección por corriente, si se hace por series de tiempo, y algunos otros experimentos que se hicieron para conocer el límite de detección, el carbón agregado durante el procesamiento de las muestras y cómo se hacen en general las correcciones antes de obtener los datos. Después viene un capítulo sobre los fechamientos por radiocarbono y el pasado humano. No hay mucha vibración. Reflexiones de un arqueólogo para arqueólogos, que fue escrito por nuestro colega que presentó ayer un polémico discurso sobre, pues, su punto de vista, ¿no?, sobre la relación que hay entre el fechamiento con radiocarbono y la necesidad y el mal diálogo que hay, pues, entre los usuarios y principalmente los arqueólogos. Bueno, él también aquí escribe un capítulo también muy polémico, muy interesante, como todo lo que hace Ciprián, acerca de los fechamientos y sus reflexiones, escrita por un arqueólogo para arqueólogos. Después también abordamos el problema de la contaminación ambiental, el carbono 14 en la contaminación ambiental. Ya también escucharon un poco de lo que hemos hecho a lo largo de estos años con la doctora Elba Ortiz. Viene otro capítulo acerca de el anillos de crecimiento, fuente de información para estudios climáticos y de contaminación atmosférica, con uno de los laboratorios asociados al LEMA, que está pertenece al INIFAP en Saltillo, y que ellos, bueno, son especialistas, en Torreón, del Instituto de Protección Forestal, ¿cómo es el INIFAP? De Investigaciones Agrícolas y Forestales, ¿no? Y pecuarias, perdón. Que no me escuche José Villanueva. INIFAP, bueno, han de saber que también tenemos algunos laboratorios que están asociados al LEMA, que CONACYT también financia para sus investigaciones, y fue una contribución de ellos. Otro capítulo habla sobre el salvamento arqueológico, datación con carbono 14 y patrimonio cultural. En este caso, bueno, hablamos sobre el papel que tiene el salvamento arqueológico, que es una dependencia del del Instituto Nacional de Antropología e Historia, que se dedica a investigar cuando se va, por ejemplo, a demoler o a construir un nuevo edificio en la Ciudad de México. El salvamento arqueológico tiene que ir a ver e inspeccionar, dada la riqueza cultural o bueno, los restos arqueológicos que existen en la Ciudad de México. Ellos siempre tienen que ir a verificar que no se trate de un sitio de importancia arqueológica. Entonces, este libro habla sobre la labor de ellos y sobre bueno, lo interesante que puede ser ese trabajo, y que algunas veces se desprecia un poco porque es nada más como un chequeo, ¿no? A ver si ya se puede construir el edificio. Sin embargo, se han hecho hallazgos muy importantes, y habla un poco este capítulo sobre cómo la Ciudad de México fue creciendo y cómo fue ganándole a la ciudad de Tenochtitlán, bueno, fue creciendo sobre el lago, y es muy interesante, se los recomiendo mucho. Después viene también dataciones de radiocarbono en sedimentos marinos. Esto es una colaboración que tenemos con gente del Instituto de Geología, de Geofísica. Ellos utilizan mucho el carbono 14 para hacer cronología de sus núcleos sedimentarios, y bueno, esperamos seguir colaborando con ellos o hacer nuevas colaboraciones. Viene lo que es un cambio de 180 grados sobre la espectrometría de masas con aceleradores. Todo esto hasta ahorita ha sido carbono 14, pero este capítulo 9 habla sobre otras aplicaciones de la espectrometría de masas, en particular en la determinación de plutonio con miras a las aplicaciones en forense nuclear. También es un proyecto incipiente que esperamos que florezca, que tenemos en colaboración también con gente del ININ, que es otro laboratorio que también es un laboratorio nacional, pero el ANAFONO, que está asociado también al LEMA. El capítulo 10 habla acerca de la dosimetría interna de plutonio, un futuro no lejano, usando espectrometría de masas con aceleradores, nuevamente con gente del ININ, con quien también tenemos una intensa colaboración. El capítulo 11 y final es pues de la gente de nuestro laboratorio, de aquí del Instituto de Física, que es aplicaciones de la espectrometría de masas con aceleradores en astrofísica nuclear, ¿no? Que es Efraín, Luis Acosta, no, Efraín no está, Libertad, bueno, en fin, entonces en resumen, este libro se propone como el primero de una serie que muestre las diversas disciplinas en que incide la técnica de espectrometría de masas con aceleradores, EMA, y por consiguiente el Laboratorio Nacional de Espectrometría de Masas con Aceleradores. Nuestro objetivo es mostrar en este pequeño libro el enorme potencial de la técnica y dar a conocer las facilidades que se pueden ofrecer en la preparación de muestras. Los dos primeros capítulos pretenden dar al lector una descripción de la infraestructura y de los métodos que ya operan en el LEMA, y a partir del tercero, los diferentes temas que se han incursionado hasta la fecha. Entonces, bueno, pues muchas gracias y espero que lo adquieran a un precio módico.
Gracias a la doctora Corina. Y finalmente vamos a tener la participación del doctor Efraín Chávez.
Muchas gracias. I will speak in English if you don't mind. Well, it's a great moment to see the end of a very long process that has been conducted by Magister Ortiz here, and with the sporadic help of Corina, and even more sporadic of my part. And it crowns an idea to have a text in Spanish. The idea is we can find these materials in English, and but sometimes this is a barrier for students, especially undergrad students. So the idea with this series of texts would be to have information available for students in Spanish. It doesn't mean that they don't have to eventually go to the original sources in English, but this is the idea to start having literature in Spanish that will be pertinent to the work that we do in LEMA. It's not supposed to be proceedings, so the idea was not to have the latest paper that you couldn't publish, but more didactic chapters addressing specific problems related to what we do here in LEMA. As Mariste said, we are planning for this to be a series of books. It took 2 years to produce the first one, so we think it will take 2 years to make every new text. And we will be looking to design the next textbook, which can include many subjects that could not be included in the first one. And you may be eventually contacted to be asked to write one of such chapters. I'd like finally to thank and congratulate all the authors and coordinators of this effort for this moment where all the effort is finally crowned. Well, thank you very much.
We are a little behind schedule, so if you have any questions, comments to the coordinators of the book, I will ask you to go them and ask directly. So there's a new chairwoman, chairperson.
Okay, so the next talk of this session is from Eduardo Andrade from Instituto de Física of UNAM, and he's going to talk about characterization of the new hybrid low energy accelerator facility in Mexico.
Hello. This presentation is part of the work of my student, Lupita, and this is part of the thesis, of the bachelor degree thesis. And also, there was a collaboration for other students associated to the LEMA, like Benito, and also Javier, and especially also the collaboration of Huerta. Okay. This is the content of the presentation. This is about just a brief description or presentation of the accelerators in Instituto. However, they mentioned it before, but here I put something more. Of course, the title is about the modification that is already explained in other talks. And the experimental part is the energy calibration of the new magnet installed in the new line. And also the important calibration of the generator voltmeter that provides the energy of the particles. Just at the end, there is some measurements made about different beams, like carbon in different charge states. This information is very important for application of the new line. And at the end is just the conclusion. Just before start, the installation of the new AMS in the Instituto, just everyone in this talk mentioned this in 2013. But also as a background, the research in the Instituto about experience with accelerators started in the 53. Here is a picture of the accelerators in the Instituto. Sorry. This accelerator originally was charged particle like protons, neutrons, and was installed in the campus just when the university campus opened in 1954. And now this accelerator was running for nuclear physics experiments for about 15 years. And when the accelerator was moved to the place that it is now, it was changed for electron beams for some application of physics. For some times, the only facility was this small accelerator. This is 700 kilovolts. This type of accelerators were built from high voltage in the 70s because the cell or accelerators dropped dramatically, and they produce this type of machines, 400 kilovolts, and they sold more than 50 accelerators for teaching nuclear physics. Most of these accelerators were sold in the United States. And this happened in 72 when this accelerator was installed. Just the new is that just this Monday officially was closed. And the CN accelerator, just the process of installation starts in 84. And this kind of machine is called CN, and it's a vertical accelerator, 5.5 megavolts. The company built, the company High Voltage built 26 of this type, and this accelerator was the second one. And the last one was installed in Arizona. And I think also in Leñaro there is one of these. But it's almost sure that this accelerator, it could be one of the last one still running. And which year was this installed? This is in 96, was the Pelletron from NEC. And just this picture is very familiar for all of us. And this is the LEMA. Now, I talk about the installation of the new line. Luis and Efraín and some people already refer to the installation of this line. The magnet, we call magnet number 3, because in this accelerator there are 3 magnets, the magnet number 1, number 2, and number 3, just for easy description. This line, the scattering chamber was bought without any equipment inside, and little by little are putting all the necessary to make experiments on this. Yes, other speakers, they will talk about the new beam line applications. Some of them are related to mainly to realize experiments with low energy particle beams, especially the interest in astrophysics. Now is in progress the analyzing one of these experiments is the nuclear reaction on carbon and carbon, and they are detecting alpha particles below the Coulomb barrier. Also, Luis just described the new acquisition system necessary for this kind of experiments where the yield particles is very small and they need to detect with large solid detectors angle the particles produced. The other Efraín made reference about the good possibility of this accelerator that the voltage can be got down to 300 kilovolts, and with this kind of facilities it's possible to produce thin targets implanted or pure isotopes like carbon-13, boron-10, etc. Other possible use of this accelerator is it could be used as most of the low energy particle accelerators for ion beam analysis, in which the material analysis is performed. The technique in English is called ion beam analysis, and such technique, the most well-known are Rutherford backscattering, energy recall detection analysis, forward elastic scattering. These techniques are very useful to measure hydrogen concentration in new material produced in the laboratory. Other type of application of low energy particle accelerators also can be performed in this accelerator is the modification of materials by ion implantation. In principle, any element of the periodic tables from hydrogen to uranium can be used to produce beams to implant the materials and to study radiation damage as a function of the particle doses. This is a well-known activity in low energy particle accelerators. Now, I skip these slides because Luis already explained about very important acquisition system to realize, especially the experiment in astrophysics, in nuclear astrophysics. Is known the simple relation there is between the voltage and the energy of the particles. Just this equation is used to define the energies of electron volts and keps and MEPs, etc. Just only an observation, the The voltage, normally, if people can measure exactly, the energy can be given by this equation. But most of the electrostatic accelerators, they don't have an absolute instrument to measure the voltage. And most of the accelerator to measure the energy is given through the deviation with a magnet, and the equation they used for this application is just in proper units is like that, where this number BR is named the magnetic rigidity and is given in kilogauss. The units here, the M is in atomic mass units, E is in MeV, and C is a multiple of the charge. Now, all the accelerators for measuring the energy is given through this equation. Actually, at the early age of the nuclear physics, this equation must be to be calibrated, and the reason was to measure the real radius where the particles are deflected. The magnet in most of the accelerators, they are measured with an instrument called by the Hall effect, and B can be measured up to 5 digital significant numbers. However, the IMS doesn't have these instruments, and the voltage and the company provides in the manual a table in which is the magnetic field and the current in the coils. From this table, it was brought, and it's a perfect linear relation where B here is the magnetic field, in I is the current in amperes. This is for the magnet, the first magnet installed. The maximum the maximum campus, the maximum field is around 14,000 Gauss. Just when people go to the laboratory, just only when Arcadio is operating the accelerator, he has just with the computer software, they use a current for a particle ion. This is a numerical example. The most used beam is carbon 14, and when the accelerator is operating in 1 megavolt, the energy of the carbon is 3.35 MeV. This 35 MeV comes from the injection of the ions from the ion source. And the magnetic field, just calculating with the equation before, is 5.35 Gauss. And using the equation, just Arcadio put the current will be 154 amperes. Now, just because this magnet was acquired a few years later, the company, the high voltage company, he said that it was built the same, was a clone of the number of the magnet number 2. However, the only information provided by the company is the radius for both magnets was 85 centimeters. And now, since this line, one of the purposes is to use for nuclear astrophysics, the energy of the particles must be very well established. And the following presentation is related about a procedure to measure the calibration of the new line and compare with the magnet installed and to check is really true the magnets are identical. And also other part is to test how well the high voltage in the tandem is provided. Just as sorry. Okay. The voltage in the tandem provides the energy of the beam to this simple equation. Here is the energy of the beam. It doesn't matter the mass. That is injected to the accelerator because the charge is just minus E. And after the beam passes through the high voltage terminal, this is stripped in many charge states, and this is the energy. And the experiments they are reported at the end is to check how well this energy is described. In other words, if the calibration provided by the company is given by this equation. Okay, the procedure about how we did the calibration of the magnet and also the calibration of the generator voltmeter. It was using a simple, a normal experiments used in particle accelerators. And maybe this was the first experiment done in the new chamber. And the procedure was to measure the elastic back scattering spectra from thick targets or carbon and silicon, measured with a solid state detector and an angle, detection angle of 135 degrees. This is just the geometry. Actually, this simple equation relates the number of particles going to the detector edge and is related to the cross section and related to the solid angle of the detector and the number of particles used for the bombarding the target, and NT is the number of nuclei on the target. This is only for, this equation is just for a thin target. And actually, this equation is used also to define the cross-section. In the early years of the nuclear physics, it was very easy to make publications just by measuring this quantity, because H are from the experiment, also this number, also the number of ions in the target preparation. And now, after maybe 80 years, there is in the web a publication of thousands of these measurements for different angles and different energies. A new application of the accelerators was the ion beam analysis of materials, and this information is crucial for the analysis of the samples. Just only here to give more details of the methods, just the nuclear reactions notation is like that, where X is the projectile, X the target, and the particle produced. Now, some special case of nuclear reaction is when both the particles before and after are the same, and this is the case of the experiment. Some of these collisions, some of them are described by a cross-section given by Rutherford, in which the energy is inversely proportional to the bombardment energy and other factors. Okay, ¿cuánto? Yes. Okay. I will go more or less soon. Now, for this system, the bombardment energy performed was in the range of 2 MEPS and down. And this bombardment energy was less than the Coulomb barrier. And they were expecting the emission spectra could be described by Rutherford scattering. But it wasn't the case. From the database called eVandal, is called Ion Beam Nuclear Data Library, the cross-section applied to describe the experiment is these two plots. The silicon, they have two resonances, and the carbon has one of them. And this information was crucial for the interpretation of the data. The normal way to measure is just with this simple standard electronics. It's not so complicated as Luis. And something when we're using this type of measurement, you need to do calibration. Is done using a triple alpha source. Now here, this is an example of two particle spectrum. The solid line is the simulation using a software called SIMRA. SIMRA means simulation nuclear reaction analysis. This code is used for the community. They apply for ion beam analysis of materials, and is very complicated code, and is commercially available. And now the procedure for using the SIMRA code, the people need to provide which type of beam is using, the energy resolution, etc. But in this case, the method, the energy of the beam, we don't know, and is extracted from the simulation. The simulation of each spectrum, the only parameter they change is the bombardment energy. And for example here, see, after the bombardment energy is taken as a free parameter, the theoretical spectrum is compared with the experimental until we obtain the best fit. In this example, this is for the bombardment of the silicon target, and the bombardment energy for this obtained was 2195, and for the other spectrum was 40 keV less. This shows the sensitivity of the method to find the energy. And this is also for a carbon, for the other target. Also from this spectrum, also is obtained the number of particles. That means for this experiment, it was not necessary to measure the charge of the particles, the integrated charge. And the sensitivity of the method to find the energy from the spectra was estimated to be minus 10 keV. And here is other example in which the same spectrum is simulated with the appropriate cross-section. And in the other spectrum is simulated with Rutherford backscattering. You can see the ABS doesn't provide any structure at all. Here is a summarize all the spectrum measured. The left is the carbon from the carbon bombardment, and the right are from the silicon bombardment. And it indicated also the energy which each spectrum was simulated. Once the energy was obtained for each spectrum, the magnetic field was obtained just from this simple equation. And the energy of the beam using the accelerator voltmeter could be calculated through this equation. And all the data was written in these 4 columns, which is the energy calculated with the voltage, and this is the energy obtained from the analysis of the spectrum, and each is the current and the magnetic field obtained from the realization of the spectrum. Just a way to present this table is these 2 plots. In this one is the energy from the spectrum, and this is the energy using the voltmeter. It could be is a perfect relation, and this is the factor of that provides the quality of the fit. And from this spectrum, this is the magnetic field measured from the spectrum and the current. Just only an observation here is the current is only from 60 to 70, and this is the equation, the fit, the data. Now it was very spectacular. The comparison of the equation from high voltage and the obtained from our measurements. Just only here can be see the could be a little different, but if we put in both equation 100 amperes, the magnetic field from the magnet from the factory is this one, 3574, and this is 3572. It's almost identical. And now, other subject was an important one, was to measure the current in the new line, and this was just only a part of what Lupita produced. Just a conclusion here is almost just given, and the important thing is the experience already with this accelerator is well very easy to change from particle beam, just because the cathode can be changed very easily, and also to change the current, the charge state of the particles that are accelerated. Look, I think a good conclusion to make propaganda for the factory is that they have a good warranty control of producing the parts, because they clone exactly the magnet. And actually, Arcadio, when runs the accelerator, the second magnet is included in the operation. And when they deflect the particle for the IMS line, it's exactly the same for the new line. This is all. Thank you.
Are there any questions or comments?
Eduardo, what would you say that is the uncertainty in the energy of this LEMA accelerator?
I mentioned the experience, it was minus 10 kV, 10 kilovolts. And something about the weight, the high voltage is produced using the Cockcroft-Walton type. They have the voltage source used a high frequency, like 100 kilohertz, and the quality of the voltage is almost constant. The Efraín mentioned in 1 megavolt, the ripple can be about 10 volts. And no? One? Wow, impressive. And nothing to do with the Pelletron or the other type of accelerators. Mm-hmm. And it's very interesting that the first accelerator built by Cockcroft-Walton used the same technology, but this technology now has put in the new level. And actually, Efraín said, for example, high voltage, the high voltage source can produce for 6 megavolts. It's almost the same size as the 1 megavolt. Mm-hmm.
Maybe a similar question to the one that Eli asked is about the energy resolution, because okay, we can run the accelerator at very low voltages,
Mm-hmm.
but then 10 keV will become a very large quantity. If we're running at say 200 keV kilovolts, then 10 keV resolution doesn't sound that impressive. Shouldn't it be a function of the energy?
Okay, it could be, but we didn't measure it at all. It's just only for the data that we did. Mm-hmm.
Well, my question was wrote by Efraín, but in the same way, which is the step that you use, because the spectra are really small, which is the step that you use to change the energy to do this measure? I mean the step in energy to,
Mm-hmm.
which is the difference between each energy that you measure
Yeah.
in keV or.
¿Por qué no lo regresa? Okay. You know, the range of the bombardment energy was, for example, here from 2.215 to 100, and it's divided in these steps. The steps was like 10 kilovolts or so.
So then, this is the resolution of LEMA, or it can be less.
It can be better, no? It can be so, okay. This gives you an idea.
Yeah,
how-
because considering, for example, resonance, the strength resonance of astrophysical numbers, important numbers, is very, very important to have a really accuracy energy to produce the reaction.
Mm.
And then, well, this is a very good news.
Yeah. The voltage, I think the Arcadio can tell us, could be changed. I don't know if they can change in 2 kilovolts or 3 kilovolts. It's possible to do it. And just to study resonance could be enough to measure very sharp resonance. Because this is digital system. And the computer, you can write the numbers.
With experiment, you check that it's true.
Yeah.
Because
Yeah.
times the number is not
Okay. Yeah,
This is very good.
for example, here, this is the bombardment energy here. The energy was changed 7 kilovolts. And the other ones, it was just random, you know. We didn't take care too much. We divided the range in 28 steps just to, the spectra show the good sensitivity, the spectra change just with a few kilovolts, measure it.
Sorry about this. I think I understood that you were changing the energy until you look at the resonance right at the end, at the right end of the target spectrum. Is that right? Because then you could, I think the spectrum can be looked at online. So you don't, I am a little bit confused. I mean, I believe that you could do that online, couldn't you?
That's here.
Right. So you just can't keep changing the energy until you see the resonance in the right end
No.
of the... No?
You just took the bombarding energy. Actually, here, we are out of the resonance.
That's right. You are below the energy of the resonance.
Yeah. And there is not
And
any
then
peak.
as soon as you start seeing the resonance, then you know what's the energy. Isn't that right?
No, but anyhow, the cross section is nuclear cross section. Actually, the resonance is out. Anyhow, the spectrum is totally well simulated.
Right.
Here, the bombarding energy is close to the resonance. But when you increase the bombarding energy, you know, the resonance go inside.
Yeah, I understand that.
And the resonance is not a sharp peak because the energy is struggling
Right.
of the particles.
So isn't it right that the energy of your beam, when you see the resonance in the right end, that gives you the energy of your beam because it's the energy of the resonance, right? And that is well known.
Yes.
Yeah, okay,
Yeah.
thank you.
Has to be. I mean, you have, because you know well where is the energy of this resonance. I mean, the thing that Eli has to say is that you know from the beginning if you start to see the resonance, which is this energy, even because you can simulate, of course, and it's very well simulated.
Yeah. Actually, the spectrum are very well simulated because the cross section are very well measured. And the only parameter they are used to simulate the spectrum here is changing the bombarding energy until the spectrum agrees with the. Okay. Actually, this work I did before for other magnets for the accelerators, and I published at least 2 or 3 papers with these methods, and I applied now for for the LEMA, and I think that it was the first experiment, the nuclear physics experiment performed.
Okay.
Okay.
Okay, so let's thank our speaker again.
Okay, gracias. Listo, gatito.
Okay, so our next speaker is Peter Hess from Instituto de Ciencias Nucleares of UNAM, and he's going to talk about nuclear clusters, the Hoyle state in carbon-12, and the like.
Eso es avanzar. ¿Y que dónde está el...? Acá. Sí. Acá y es avanzar. Inglés. Yo preparé para español, pero voy a hablar en inglés. I will do it in English, but it may be that I switch to Spanish in between. Okay. Okay. Well, this is this one. The content is that I will present a model, which is a cluster model, where we try to look at a nucleus as composed of clusters, like 2 carbons give magnesium-24. In this case, a carbon nucleus composed of 3 alpha particles. Then I will apply this model, which satisfies Pauli exclusion principle, to carbon-12, and I will discuss how important is the Pauli principle. Then I will talk a little bit about geometrical mapping, but that I will pass over quickly because it's trivial, and then I will give a resume. These are some reports which are important. For a nice report about light cluster systems. And excuse me? This is published, but I didn't have the time to look at it in detail. It's published. It's an older talk I have here, and this one, which is a very nice model, which is a completely microscopic model. The model I will talk about is an algebraic model. It is called the semi-microscopic algebraic cluster model. Microscopic because the space will be microscopic. Semi because it will be phenomenological. The Hamiltonian is phenomenological. Phenomenological models have the advantage that you can do a lot of calculations which are more difficult in exclusively microscopic models. But they are not as fundamental as real microscopic models, the macroscopic Hamiltonian. The cluster is composed of, or the nucleus is composed of A particles, and the A is the sum of all particles in the K clusters. And it observes the Pauli exclusion principle. How it does it, I will show in the next transparency, but here I will look at an example of 2 clusters. So you have the 2 clusters, and they have a relative motion. The relative motion is described by boson creation annihilation operators, where m is plus minus 1 and 0, which I forgot here. And we introduce artificial boson, a sigma boson, which has no physical meaning. It's only trick to introduce a cutoff, because when you require that the total number of bosons is conserved, the n pi, which interests me, goes from 0 to this maximum number n. So it's a cutoff. And the trick, the advantage of the trick is that the Hamiltonian has to conserve the total number of bosons. The Hamiltonian has to be a function of generators of a group, and it is related to symmetric groups, and it is simplifies enormously the calculation. But we have to introduce this additional boson. How to satisfy Pauli principle minimally? This I have shown here as an example: alpha particle plus oxygen. The alpha particle has 4 nucleons in the n equal to 0 shell, so L is 0. It doesn't have any quanta. Oxygen 16 has 12 particles in the p shell, so it has 12 quanta. And the neon 20 I want to describe, which is composed of the 2 clusters, has 20 plus 8, because each of those carry 2 quanta. So it has 12 plus 8, 20 quantas. The 2 in the sum has 12 quantas. So when I want to describe neon 20, I cannot just put the 2 clusters together, because they would have only 12 quantas. It amounts to put 4 nucleons somewhere here, but it's already occupied. So we need to shift these 4 nucleons up here, although the sentence is not very well set, because all the nucleons are antisymmetrized. I cannot tell are these 4 nucleons. Once you put them here, it's antisymmetrized. The important thing is you need at least 8 quanta to satisfy minimally Pauli exclusion principle. Most phenomenological models which are published on this, which don't take this into account, violate Pauli principle. They put the 4 quanta somewhere here, so they don't tell it explicitly. Now I will shock you with this transparency, but it is a very easy talk, because you have an SU3. SU, unitary group, means harmonic oscillator of n dimensions, 3. So it's a 3-dimensional harmonic oscillator. It means you have the oscillations x, y, and z. So this describes the shell model of the cluster number 1. This describes the shell model of cluster number 2. Forget about this. This has to do with the total number of quanta. And you have the relative motion, n pi 0, is also an SU3, because the relative motion has also 3 degrees of freedom. To which this amounts is to couple the representation of the shell model of cluster 1 with cluster 2 with the relative motion, and you put them together and you get a whole bunch of lambda mu's. The important thing is here you implement Pauli exclusion principle, the Wildermuth condition, which I have mentioned before. So n pi has to be larger or equal than the minimal number of quanta. And also I put here a cat in order to indicate that I don't construct the function explicitly in a spatial representation. All I need is to construct the quantum numbers. And then I create a cat. And that's easy, the simplification of SACM. You only construct the quantum numbers and assure that they correspond to states with observes the Pauli exclusion principle. Then Wildermuth condition is not sufficient to satisfy Pauli exclusion principle. Even if n pi is greater or equal than a minimal number, you have a lot of representations which don't satisfy them. So what we do is we go to the shell model, which is this one. We construct all possible excitations, construct all representations. So we have a bunch of representations, and then we compare it with a list, and only the overlap satisfy Pauli exclusion principle. So if 1 lambda mu is in the shell model, it satisfies Pauli exclusion principle. It's not toucher. You erase it. It's a very easy way. It's completely algebraically. You can do it even by hand if this is very simple. If these representations are a little bit more complicated, you can even still it by hand if you would be crazy. But we wrote computer programs which just do the counting. It's nothing but a counting. So this constructs the model space of this model, and this model space is microscopic. However, the Hamiltonian is phenomenologic. We write them in terms of generators or Casimir operators of the group which appear here. So if you draw here a line, these are all SU3 generators. And pi is a shell model. It's a number of quantum of p bosons, so it's a shell model. H bar omega is fixed by the shell model. It's not a parameter. The C2 is the second order Casimir operator of the SU3, and you can prove that it is proportional to the quadrupole interaction. There is a contribution of L squared we can eliminate here, but essentially the quadrupole interaction. Therefore the minus sign, so it deforms the nucleus. This is the third order Casimir operator, which serves to distinguish lambda mu with 2 mu lambda, and this is L squared. If you have a band which goes like L times L plus 1, this is the eigenvalue of that, You have only A, so A is 1 over 2 theta. Theta is a moment of inertia. But the moment of inertia may change depending on the L, if it's even or odd, or depending on the excitation, because when you excite the nucleus can be deformed, and so the moment of inertia changes. This is a k-squared operator. K is a projection in the intrinsic system of the nucleus, the z-axis, on the z-axis of the angular momentum, and it serves to distinguish spins which are in the same lambda mu representations. Up to here, everything is analytically. I can write down immediately the eigenvalue, but nature is not so kind to us. We have to mix several shells, because they mix several shells. So delta n is equal to 2, or plus minus 2, or you have p dagger with Hamilton conjugate pp, it just stays the same. So the last term breaks the SU3 symmetry. Or going to 3 alpha systems. So this is a cartoon of mine, not very well written. I'm not Van Gogh. So this is the distance between the 2 alpha particles and the distance of the 3rd alpha particle, center of mass. But also this nomenclature is wrong, because the alpha particles are identical. You cannot say this is 1, 2, 3. You have to symmetrize them. Even you can change, define lambda in any way you want, and rho in any way you want. Rho can be this or can be that, and so on. This is only for illustrative reasons. When we go to the subsystem of 2 alphas, these are the clusters, which I denote by C lambda rk mu ck, but they are alphas. They have no structure, 0, 0. So you have only the relative motion. So the only representation you get n rho 0. But the system of 2 alphas is beryllium 8. The 2 alphas are identical. You have to take into account when you interchange them, you cannot distinguish them, and this leaves its symmetry property of the harmonic spherical harmonics, and so only n rho even is allowed. Also, if you look at the minimum number of quanta is 4, because this has none, beryllium has 4 quanta, 2 nucleons in the p shell, so the n rho has to be larger or equal than 4. When you go to 3 quanta, you can have the n rho 0. This 3rd alpha particle has no structure. You can multiply by them. It is also 4, because beryllium has 4, carbon has 8, so the difference is 4. And you can now construct all combinations of them. This is, of course, more richer, and rho has to be at least 4, 0. It can be 6, 0, and then you have to multiply it by that. Fortunately, Moshinsky did the job for us. He constructed the complete the symmetric system, the states which are symmetrized, which symmetrize 3 identical particles. It can be alpha in that case. So we did it. I don't show it here because it's a little bit of mathematics, but this is a space we finally get. And then you can see already some structure. You have 0, 4. This has only k0, so you have in 0 quanta, delta n is 0, so you have the valence shell, L0 to 4. Then you have the first excited states. The even states are parity positive, the odd states are parity negative, so it's parity negative. You have this kind of 2 bands, one of case 1 and 3, and then the next one you have this kind of band with this constant. From this you can already see you have at low energy only 1 5 minus state, not a second one, which other models claim. There is a next one, but it's a higher energy. It can maybe go very down, but it is very unlikely that it goes so far down. This is not this 5, this positive parity, this delta n equal to 3. Also, you can see that the states here have completely different internal structure. So you cannot join these two sets of states within a band, because what means a band? You have a nucleus of a certain deformation and you rotate it. You don't change the internal structure. But here, the internal structure changed, so you cannot associate 2 different, one and the same band is done by other models, because if you do a classical model, 3 alpha particles, and without any internal structure, this is like atomic physics, then you have a triangle, and you can rotate the triangle, and then in this case, you can join the states to the same band. But we are in nuclear physics. We have Pauli exclusion principle, and so you cannot join it. And also the internal structure and deformation is completely different. So here, geometrical mapping. I won't go into the detail. I want to say you have a Hamiltonian. You take some trial state. It can be bad. It can be excellent. You calculate the expectation value. And you know from quantum mechanics course, if you look for the minimum of that, you have an approximation of the ground state. The Ritz variational principle. But you can ask what happens when alpha changes a little bit. So it looks at the response of H when you change the alpha. And alpha you can relate to some collective variable, in this case the distance of the two clusters or three clusters and so on, as more alphas. So this defines your classical potential. And when you calculate them, you can have a geometrical mapping. The potential tells you what it is. Well, I won't go into the detail here. It turns out it has to be a triangle, equilateral triangle in the ground state. But that's not a surprise, because you have three alpha particles. The three alpha particles are not distinguishable. So the distance of particle 1 and 2 has to be the same as 1 and 3 and 2 and 3. And the only system which can do it is a triangle. So nothing wow about it. It has to be a triangle. In the ground state, because when you have excited states, you have more possibilities. And this is shown here. This is a microscopic calculation by Freya, Horiuchi, and so on. And this is the ground state, and it looks like three alpha particles. But be careful. This is not an alpha particle. This is a density peak you have here, and another density peak, another density peak, with a large overlap. So this is a whole system of 12 nucleons, which are antisymmetricized, which shows by some excellent peak, which some people associate to alpha particles. If the two alpha particles would be very well separated, then you can say the overlap is small, and you can put a box around it, and this is an alpha particle. Only in that case. But you see already in the next excited state, the second CO plus state, this is a Hoyle state. The CO plus looks like a triangle which is a little bit more extended, but already the 2 plus is completely different. It's not a triangle. It's some kind of line and so on. And the 3, it is completely lost. So this model is better than the SACM because it's fully microscopic, but cannot calculate all the states which are possible. We did within the SACM the calculation where we looked at SU3, and we tried to adjust the transition from here to here, which belong to 2 different SU3 representations, therefore it's 0, the transition. And we tried to put in the mixing, which I showed you, and try to adjust 1 and 8. The more mixing it is, the more difficult it is to getting to adjust. It's just a practical matter. It doesn't mean that the model gets wrong. It's just more difficult to adjust, or we have to introduce more parameters, but we want to keep the parameters small. Here you have the experimental value, and here you have the theories, different versions. As a quadrupole operator, we use now a quadrupole operator, which is a physical quadrupole operator. Again, in classical mechanics, Goldstein, you learn that the zero component is 2 zeta squared minus x squared minus y squared. When you quantize it, you have a term which doesn't change the number of quanta, a term which changes the number of quanta by 2 or lowers it by 2. Raises and lowers it by 2. So this is a type of operator you get. The P refers to the sum of the relative quanta in rho and in lambda. The physical quadrupole is that. Normally one only takes that, which is justified if you look only at the valence shell and think that the excitation to higher shells is not important. But in the Hoyle state it's important. You cannot neglect these contributions. Here is a calculation. This is experiment. This is the Hoyle state. The Hoyle state is, by the way, very important. Without this state we wouldn't be here, because it's very important to explain the fusion of 3 alphas to a carbon with a high sufficient probability. If it wouldn't be there, it wouldn't produce it, and I couldn't talk about it, so it must be there. This is pure SU3, and you see the reproduction is quite nice. You also see you have 1 5- state. You have not another 5- state, which produce other models. And I will talk a little bit about the nature in a moment of the Hoyle state. Here you have the adjustment to 8 to 1 Weitkopf unit, so the experiment is 8 Weitkopf units. You see that the adjustment gets not as nice, and with here you have case 1 and case 2, case 8. Case 1 means adjust to 1 Weisskopf unit, here to 8 Weisskopf units is a physical one, and you see even the 8 is a little bit better than that one, but it's a matter of how to adjust it. No? But you see here, this is a calculation of oblate top model by Rudolf Beike and Jakello, and you see they can describe some states. You have, for example, here an agreement, the degeneracy to minus to plus as here, but all the others, degeneracies are left. In general, you have less states here than here. This is an effect of neglecting the Pauli exclusion principle. You have a second 5 minus. Here's no second 5 minus, and so on. And you see, if you approximate it by a triangle, classical physics, some of the low states you can get, but you cannot get the complete spectrum. You just don't fit it. Here is a pure SU3, but adding more states, which come out of the theory. And here you see the Hoyle state comes in SU3 from 8 oscillation quanta, not from 4. So it's delta and P is 4, not 2. It comes from a high state. This is an agreement with calculations of no core shell model calculations by Trier and others, which show that we have a large, high number of oscillation quanta contributions. That the states come down so low is due to the large deformation of the carbon nucleus. The quadrupole index is very large, so it pulls states from very high energy to low energies. Another thing which the oblate top model doesn't mention and the others cannot calculate, if you have a state from high shell number, positive parity coming down, that should be also from negative parity coming down, and this here one. And in this SU3 limit, it is degenerated with the 1 minus state here. So it must be there somewhere. It may be, because it's a model, maybe a little bit higher, lower, etc., but it must be in the vicinity, is a prediction of the model. Now look at the content of the states. This is the ground state, and this is the percentage contribution from these representations. You see, the ground state has 2 main contributions from here and here, here and here, and the second 4 plus norm is associated to the Hoyle state and the first to the other state. But they are very near. You can change them easily. And you see that it's better to associate the 4-1 to the ground state. Though at higher excitations, they already diverge. It means that the internal structure of the state changes. And this is the effect of large deformation. Really, it's an approximation to associate bands, because the bands itself don't follow exactly L times L plus 1, and there starts to be mixture with other bands. And here's the Hoyle state, and you see the Hoyle state comes from delta and pi equal to 2, delta and pi 4, different one, and astart until delta and pi of 6. Dreyer has an average contribution between 8 and 10, but in order to describe the Hoyle state exactly, microscopically, had to go up to 20. So Hoyle state is a very non-trivial state which involves a lot of excitation, shell excitations. Here you have the negative parity states, and you see they are more or less equal. So this is case 1, case equal to 3. But here are some differences, which means that they have some difference, but at the low contributions they seem to be nearly equal. Here is when we adjust it to 8 Weisskopf units. This is an experimental value. And you see the same thing. Here now this second to 4 plus state is more associated to the ground band, because they are very near. If you have this or this, it doesn't make many differences. And this is the Hoyle band. And again, the Hoyle band, you have contributions. You see here from the 10, the most contributions from 10. So you see the tendency is going to have contributions from very high shells. This same negative parity states. Okay, conclusions. I shortly presented the semi-microscopic algebraic algebraic cluster model of the nucleus. for light nuclei. I showed that with simple argument the carbon-12 has to be a triangle with no surprise. And I applied the model to carbon-12, which includes a principle of Pauli principle. And it means the spectrum is more extended, it's less dense, because the Pauli principle tends to repulse states. And there are various problems which I don't discuss all, conceptual problems of Loeb top. It is a model which does not satisfy Pauli's exclusion principle, or you can say it describes some states with states which don't exist because it don't satisfy Pauli exclusion principle. So the Pauli exclusion principle is important. Now we are calculating oxygen 16. Again, there this model, this classical model, describes that it's a tetrahedral. Of course, you have 4 particles in the ground state. All the distance of all the alpha particles have to be equal, so it has to be a pyramid. But the excited states are less. Again, we find, we haven't written it down yet, or we're starting to write it down, that spectrum is not as dense as shown in that model, and there are some important differences. So in order to show if a model is correct or not, it doesn't suffice to just measure 1 5- states and say, wow, it must be a triangle. It's just there because it belongs to a band. You have to measure all the states at low energy, and this is a tough thing to do. But one has to do it. Thanks.
Comments?
Thank you, Peter. Can you show us again this density plot that you have for the ground state and the whole state, where you see?
This is not my plot. It is from Freer, but it's a nice thing because they construct explicitly the states in the space representation and anti-symmetrize it and so on. So this is a plot.
Because, well, one of the subjects that we are interested in here, because of the low energy that we have in the machines, is to measure the size of the nucleus.
Yeah.
So apparently there would be a way to predict the size of carbon-12.
Yeah.
So
yeah, if you use the distance which we calculate, which agrees more or less with that one, but this of course more to trust. It's more or less of the same size. I don't remember the number, but I can tell you we have written it down, and they predict the size. It's of course here it's a triangle in the ground state.
And that would be a density. Some sort of a density?
Yes, well, a density is not spherical, as you see here. Okay. It is something like a triangle, but you can discuss what is the distance from here to here, or from here to here, and somehow to average over everything. Okay. But it's very nice here. You see it is the states in the ground state maintain the same structure, more or less. So here you have a right to say that it's a rotational band. Yeah. Here it's a little more doubtful.
Okay. And finally, one other question is, looking at the last comparison that you did with the spectrum, the theory and the experimental. Well, the last spectrum that you show with the
this one. Here it's SU3. I don't have a mixing.
No,
here
you showed one last one, right?
And this one.
Right, that one. So that's the SU3 with old states, right?
This SU3 without the mixing, so one B2 value is wrong. Okay. It's 0. But the nice thing about it, the spectrum looks nicer. No? It's easy to calculate. But also in the other calculation, when we mix it, this state moves a little bit.
Okay. Because those states are very close. So
what is normally plotted are these states with the 5-. This, I think, is not measured, and this is not measured at all.
Hard. Tough.
Well, in the publication, in the FISREF letters, which one of member here participated, I see a peak and a small side peak. I ask him if this matters something, but as experimental physics say, this is an error, this is statistics and things like that. But for theoretical physicists who want to provoke, I say maybe you have measured this 1 minus. But I'm not an experimental physicist. But I know the tricks, so don't fool me.
Okay, any more questions or comments?
Peter, I think this will probably be a silly question. You know about the Borromean nuclei. You have 3 clusters, and they have the property that if you take a cluster away, the other 2 are not bound.
Yeah.
So something like that happens here, because if you have 3 alphas, you take 1 away, you will have a beryllium 8, so that's unstable.
Yeah.
But could this be called Borromean? I mean, I don't think so. Right?
Well, here the model assumes stable systems. I cannot calculate decay rate. Then I have to do something more. I have to take an half matrix formalism to connect the inner part, which is this model, with the outer part, which we haven't done. Many years ago I tried to do that, but the student left, so I left it too. No? We cannot describe decay rates. If you want to discuss something which you mentioned, we have to be able to describe decay rates. There is some algebraic operator which can describe decay rates, calculate spectroscopic factors, but this is not dynamical one. This is just an adjustment to some values, no? Some approximation.
No more questions? If not, let's thank our speaker again.
Sorry, I have to leave.
Okay, and then we move to the last talk of this workshop, which is going to be given by Javier Miranda from this institute, the Institute of Physics. And he's going to talk about ionization induced by heavy ion impact cross-section measurements at LEMA.
Buenas tardes. ¿Sí? Buenas tardes. Okay. Con esto de los cursos de modelación, ya pues aprende uno a pasear en las pasarelas. ¿Cómo? Okay, thank you very much. Actually, the title was missing a colon here. So this is ionization induced by heavy ion impact and cross-section measurements at LEMA. And I must be really very grateful to the group that is responsible for the operation of the laboratory, because they actually invited me to propose some experiment regarding the things I know how to do, which is measuring cross-sections, X-ray production cross-sections. So now I know it is very comfortable to go to a laboratory where everything is working and everything is installed. So I only need to connect an X-ray detector, a particle detector, and everything goes smoothly. So, okay, the outline of this talk, I hope it will be short. First, the motivation for these experiments. I will say a little bit about what X-ray spectrometry is, the experimental setup at LEMA for the X-ray spectrometry, the first experiments that were carried out about 1 month ago, and when can we expect in the future for this kind of experiments. Well, the motivation is the use of X-ray spectrometry at this institute has been performed in the mid-1970s. Actually, we have, I think, at least one researcher that used to work with PIXE in the early, the mid-1970s. Eduardo used to work with, I think he was in charge of buying the first silicon lithium detector for to work with in Maria, the laboratory which has been already shut down recently. So PIXE has, but there was a problem. PIXE has not been used consistently. PIXE is this technique using protons or ions, positive ions. It has not been used consistently at this institute since almost more than 10 years ago, for reasons I don't want to explain here, technical reasons, let's say. So the operation of LEMA is a very good new opportunity to apply PIXE again. Probably not as a routinary analytical technique, but to do some atomic physics experiments. Also, I had to find out what problem has not been really studied about X-ray production cross-sections, and that can be studied at LEMA. So oh my God. Well, it's not working anymore. So if I was Darth Vader, I would be deaf, probably. There's no laser anymore. So there is not a very good knowledge about the isotope influence in the projectile, of course, on the ionization cross sections. Okay, let's see. Okay. There are only a few experiments comparing the cross sections using protons and deuteriums, and also helium-3 and helium-4 ions. So it would be interesting to use some other isotopes that can be produced at LEMA. So, well, what is X-ray spectrometry? First, I want to show a simple cartoon here. We are thinking of a very simplified model of the atom. We have the nucleus with the electrons moving around the nucleus, having having the discrete energy levels, and so we irradiate this atom with primary radiation, I'm making here, it was on purpose that I wrote primary radiation because we can use, thank you, we can use here either positive ions, we can use electrons, or we can use X-ray photons to produce a vacancy, to produce a ionization in the deep shells of in inner shells of the atom, so we can expel an electron from this shell, and we may have the atom remains in an excited state, so an electron from an upper shell fills this vacancy, but there is still an excess of energy in the atom, which is expelled by the atom in the form of an X-ray photon. Of course, the energy of these photons are characteristics of the atom that produced this photon because of the discrete or the characteristic energy levels in the atom. So, thank you. Sí, pero iba a tomar agua, perdón. Sorry. There is the emission of an X-ray photon which has a characteristic energy of the atom. So this is also a very simplified diagram of the electronic energy levels in the atom. Usually we give the name of the X-ray photon depending on where the original vacancy was produced. In this case, if we expel the electron from the K shell, the most bound electrons in the atom, we call the K line. And depending on the intensity or the probability of the transition, it was usual to give names alpha, beta, and so on. So when the spectrometric methods were better, it was possible to identify two lines in this K alpha, and they came from two different transitions from the L shell, from the L2 subshell and the L3 subshell. The L1 to K transition is forbidden because of the transition rules in quantum mechanics. So we have different probabilities for the transitions depending on the different shells where the decaying electron is coming. When we produce the vacancy in the L shell, we have a lot more combinations for transitions, so we have a much more complex spectrum. And finally, well, not finally, there are more possible lines. When the original vacancy is produced at the M shell, there are many other combinations, and I am showing only two transitions here for the M lines. So how does a spectrum look like? This is also a cartoon. We think of this possible transition, an atom. We have an electron in the K shell. We have electrons in the L3 subshell, and we have here, let's say, a proton or an ion. So let's assume we have also a detector here, a solid state detector, and some nuclear electronics connected to this detector. So we can think of the incoming ion producing this vacancy at the K shell. So the electron from the L3 subshell fills the vacancy, and we start having, if we repeat this process many times, we have a lot of X-ray photons coming from the atom to the detector. The detector produces an electric pulse that is processed by the electronics. And finally, we have something like this, This is an X-ray peak. We can see this because it's a random process. We see something like a Gaussian curve. And the energy is the maximum here. We call it, as you saw earlier, we have here the K alpha 1 line. And the energy is defined by the difference in the two electronic levels, K to L3 levels. And so this is the energy of the K alpha line. When we have several elements in our target, we may have different lines. We usually have, when we have the K alpha line, we usually also have the K beta line. And we have 3 elements in this case, and we have the K alpha and K beta lines for each element and different energies. These energies are characteristic of the elements, so we can identify them for quantitative analysis. Or if we have pure elements, we will have only these 2 lines. So this, how can we apply this spectrometry at LEMA? It's as I said, it is very simple because they have the staff, the group has already made the hard part. So I just came with my detector, X-ray detector, and our sample positioning system. This is a simple diagram of how we positioned all the components of the system. We have an X-ray detector here located at a 45 degrees angle, and also a particle detector to detect simultaneously X-rays and the backscattered ions. We have here samples that usually are in the form of, for these experiments at least, in the form of thin films. And a Faraday cup behind the target because it's a thin film. Usually thin pure elements or pure compounds deposited onto 3.5 mylar substrates. And they have 25 millimeters diameter. So we can position 3 samples at the same time. Here is the electronics and a beam collimator. I think the dimensions are about 20 centimeters, 30 radius. So what we need to measure then is, this is a picture of the detector, the X-ray detector. It's a very small one. This is the technology that is used today. Not today, they are much better. It's the technology that was used 20 years ago for detecting or analyzing soils in Mars. So these are much cheaper than the old silicon lithium detectors. In this case, we have a silicon PIN diode, which has an active area of 13 square millimeters, protected by a 25 micrometers Williams window. And we usually protect here the detector with a 12 micrometers thick mylar film to protect it from backscattered protons or ions in general. So, it is cooled by the Peltier effect, so an electronic process, so it needs no more liquid nitrogen. These are very small detectors. And we have here also our feed-through to insert this into the chamber, the irradiation chamber. We connect this feed-through in this position. So our first experiments, first I need to mention only two of the theoretical models used to describe the ionization process. The first one is the plane wave-borne approximation. It's very, I think, we saw it in our courses in physics. I will not enter into the test, but we think of the projectile as plane waves when it goes into the target atom and when it is scattered after the interaction with the atom. There are several conditions for this approximation to work. We need to think of the projectile as a point charge. We need to consider that the initial and final waves are plane in the whole space before and after the collision, and that the electronic states are not perturbed. The bad news is that it doesn't really work for real X-ray production cross-sections. So there was an improvement called the ECP-SSR theory. It has nothing to do with the Soviet Union, of course. This is the name because of there is an energy loss consideration of in the projectile during the collision, a Coulomb deflection that is expected because of the proton is scattered by the nucleus. The electronic states are perturbed because of the presence of the projectile, so a model or a method known as the perturbed stationary states, PSS. And finally, the bound electrons in the atom are sometimes, the inner shell electrons have relativistic velocities, so it is necessary to make some correction because of these relativistic effects. So we have here the ECP-SSR theory, and when the exact limits of integrations in the theory are used, the authors of this model decided to change this capital E to lowercase e. It makes no difference really, but they are very proud of this advancement. Well, how we measure this? Well, we design an experiment, a very simple experiment to show ourselves that this system is useful. So we chose energies, proton beams with energies between 1.3 MeV and 1.8 MeV. We measured the efficiency of the X-ray detector using these thin film standards. The energies of this of the K alpha lines of these elements cover a range for where the energies of the L lines of these elements are contained. So we try to measure the L X-ray production cross-sections of strontium, yttrium, zirconium, niobium, and molybdenum with atomic numbers between 38 and 42. This experiment has been done several times in the past by other authors, so we only try to check that it is possible to do trustworthy experiments. So I will not spend too much time here. We measure, as I said, simultaneously the X-rays produced by the element and the backscattered ions, backscattered by the thin film targets. So we have here the efficiency. First, we need to measure the efficiency. This is the efficiency, the number of X-ray photons that we detect in the line of interest from the standard. This is the solid angle of the particle detector. This is the backscattering cross-section. We can use the Rutherford cross-section corrected by some electronic shielding. This is the cross-section for the K alpha lines of the standard, which is very well known, and the number of backscattered protons to the detector. And once we measure the efficiency, we use it here to measure to determine the cross-section of the L line. Here we have the number of X-ray photons in the from the target, target, and the backscatter protons. All this is already it changes also because we have a different element, target element, but this is the same, and this is the efficiency we already measured. So this is an example of a backscattered ions spectrum. This is for niobium oxide film deposited onto mylar. Here we have the niobium peak, and the oxygen peak here is superimposed to the mylar signal. So we integrate this peak, so you can see it is very fairly easy. And this is an example of gallium phosphide standard. Here we have the gallium K alpha and K beta peaks. We have the phosphor K alpha and K beta peaks. It is impossible to resolve the K alpha and K beta. We have an spurious signal from aluminum. Okay, yep, thanks. And we have seen that mylar films, mylar substrates are always contaminated with calcium. So this is also this is useful to calibrate the energy of the spectrum. So we also, you can see, we can integrate these peaks fairly easily. So this is the first efficiency measurements at LEMA, X-ray detector efficiency at LEMA. Here we have the aluminum and silicon X-rays. We have here a step because of the absorption edge of the X-rays in silicon. This is equal to the K-shell electron binding energy. And these are the remaining elements. We can make a fit. You can see that this is very nice. This is what we call the spoon, so it is very simple. And these are our first results. They are very preliminary. So these are our measurements. For strontium only, these are the total X-ray production cross-section for the energies. Actually, it was not 1.3, it was 0.335 MeV, if I'm not wrong. So, so these are our results. These are the results by other author from Argentina, and these are very old results by Jerry Dogan. And this is the prediction from the ECP-SSR theory, and using Campbell atomic parameters that we need to convert from ionization to X-ray production cross sections. You can see that the first approach is. I would say it is very good as compared with more recent experiments. Well, what can we expect for the future? We would like to measure the cross sections using two different isotopes that I hope you can produce at the accelerator, like beryllium-10 and beryllium-9. For the K X-ray production, K-shell X-ray production cross sections of iron. In this case, these are theoretical predictions. We expect to have some difference, some measurable difference between these two cross sections. This is a logarithmic scale, so you can see it may be possible. And also for carbon-12 and carbon-13. It has never been measured in the past, this difference. Although there are many measurements of the K-shell X-ray ionization using carbon-12, it has never been measured using carbon-13. So this may be an interesting experiment to do. This is useful to see if the theories are correct, actually, and to see some other, I did not mention here, but some atomic parameters can also be studied by the measurements of these cross sections, involving the electronic transitions between the different electronic shells. This is the ratio of these cross sections from beryllium-10 to beryllium-9. and carbon-13 to carbon-12. So for carbon, we would expect a difference about between 10% and 30% perhaps. And for beryllium, we would expect something between 35% difference in these cross sections. When I calculated this curve, I did not expect this bump here. There is no, so as far as I know, there is no explanation of this. So this would be a very good opportunity to determine if this is true, if this is a real phenomenon. Final comments. The operation of the LEMA opens new opportunities in the study of the atomic inertial processes. We can also apply all these methods to the L-X-ray production cross-sections, which are much more complex, but they are much more funny. The high projectile mass resolution of the accelerator may allow a better understanding about the influence of the isotopes. It is not very common to have this difference or this mass resolution in other laboratories. And we should be able to determine experimentally the differences on these ionization cross-sections or X-ray production cross-sections, which are closely related, due to the different mass of the projectiles. So we hope we can do soon more experiments as soon as you have available beam time. Of course, it's and we have targets, by the way, also. We need to prepare some targets, because when we use heavy elements, if we want to have the mylar films, they are very, very quickly destroyed by the heavy ions. So we usually use carbon, thick carbon substrates and a thin film deposited on them. We have done that many times in, by the way, with a lot of experiments there. And well, finally, I need to thank the people that helped, that contributed to this short work. Juan Carlos Pineda, for his patience, because I had to go to class and he stayed several hours. Arcadio Huerta, of course, for having the patience to give us the beam with the energies we wanted. Daniel, Luis, and Efrain helped a lot to install all the detectors and the electronics and so on. And all my students, physics students, I don't want to, pardon me? No, the only person, the only student that is here did not work in this experiment. Curiously, she's the Earth Sciences master. Salvador, Enrique Hernandez, Juan Antonio Mendoza, and a new social service, Derian Serrano. And that's all. Thank you.
Comments?
Could you tell us, Javier, well, first, congratulations, because it was really fast mounting of this technique in LEMA, and you measure really fast, in fact. And my question is, which is exactly the reason of that your uncertainty bars in your data are less than the previous one?
Probably because we had a better statistics both in the backscatter ions spectrum and the X-ray peaks.
Okay, and then it's related with the statistics.
Statistics, and mostly it is because of the uncertainty and efficiency, which is mostly due to the uncertainty in the thickness of the standards, which is 5% in the standards, and we had a little bit of the uncertainty also in the solid angle of the particle detector. If we can measure it
related with detectors?
With the particle detector mainly.
Okay, particle detector.
Yeah,
the PIPs.
Yeah, but if we go into details, if we look at it carefully, we can cancel this term, the particle detector solid angle, because it is included in the efficiency, and then we use the efficiency in the one above and one below in the quotient. Yeah.
Javier, when you show your cross-section efficiency for carbon 13 and 12 and beryllium 10 and 9,
This one?
you say that experimentally you can.
I would
see this
expect.
difference, but I see that the cross-section are very close. Do you think it's possible? No, the previous one.
Yeah.
Do you think you can?
Yeah.
You can have this enough resolution to distinguish?
I think so. It is related to the question posed by Luis. We have less than 10% uncertainty, or around 10%. If you see here, the difference is from about, let's say, 30%. This is a logarithmic scale.
I see. Okay.
You see? Yeah. Mhm. Yeah. And as I said, we have about 35% here for beryllium, but I do not understand this bump. I need to ask Lapiki if it is real.
No more questions or comments? If not, let's
No.
thank our
Thank you.
speaker.
Well, with this, we conclude the works of the workshop, and it's been a real pleasure to have all these wonderful talks. So I